looked at certain important properties of Laplace transforms in the last lecture. The particular properties which are of interest are those when f of t gets multiplied by t, what happens in the transform domain. If f of t is differentiated, if f of t is integrated, their effects in the transform domain are three important properties which we discussed in the last lecture. We will continue this discussion of the properties of Laplace transforms, which will be useful when we handle problems involving the application of Laplace transforms to the solution of electrical networks and systems under dynamic conditions. So, let us consider now the next property, which concerns what is called shift in frequency. Shift in frequency domain, that is S domain, which is equivalent to multiplication by an exponent, multiplication by an exponent exponential function in time domain. What we are going to show is that if you multiply an f of t by an exponential function like e to the power of minus alpha t, it corresponds to a shift in the frequency domain, that is the S plane or S domain. Let us consider an f of t whose Laplace transform is f of s. The question which we would like to ask is, what is the Laplace transform of f of t multiplied by e to the power of minus z t, assuming all these, of course, assuming that f of t is a causal time function. What is it equal to? To make for generality, z can be complex. So, this is the what we are going to look at. So, to using the formula for the Laplace transform of a time function, this particular Laplace transform would be from 0 to infinity f of t e to the power of minus z t e to the power of minus s t dt. I am not putting specifically 0 minus, because depending upon our interest, whether you take from 0 minus or 0 plus, depending upon what you take f of t to be, the type of f of t that you are interested in. So, we will leave it at that. This, of course, can be written as 0 to infinity of f of t e to the power of minus of s plus z t dt. Now, you see that if it had been e to the power of minus s t dt, f t e to the power of minus s t dt integral will be f of s. All we have now is instead of s, we have s plus z. So, if it had been f of t e to the power of minus s t dt, this would have been capital F of s. This is Laplace transform of f of t. Now, instead of the variable s, we have s plus z. So, this will be f of s plus z. So, we have, if f of t has the Laplace transform f of s, if you multiply f of t by e to the power of minus z t, the Laplace transform is simply f of s plus z. That means, this is a translation or shift in the frequency domain. So, this is a very important property which will be found quite useful in finding out the Laplace transform of certain time functions, as well as the inverse Laplace transforms of certain functions of s. And of course, in the new function that you are having, the abscissa of convergence, whatever it was for f of t, will get modified because of this, the factor e to the power of minus z t. Depending upon the real value of z, then the abscissa of convergence can be modified for the new function, but that is not important for us. We note, of course, that it is possible that the abscissa of convergence of the new function will be different from the abscissa of convergence for the original f of t. Let me take an example. suppose we have u of t, we know that its Laplace transform is 1 over s. Now, let me multiply u of t by e to the power of minus alpha t. So, according to this rule, instead of s we have to replace s plus alpha, that is all that we have to do. Therefore, this is 1 over s plus alpha. So, in other words, e to the power of minus alpha t u t, which we have derived earlier from fundamentals, could have been derived using the applying this particular rule of shift in frequency domain corresponding to a multiplication by e to the power of minus alpha t. Now, let me take another example. Suppose I have cos omega naught t u t, a cosine function. We know its Laplace transform is s over s squared plus omega naught squared. That would be a cosine, a trigonometric function which starts from t equals 0. On the other hand, suppose I take e to the power of minus alpha t cos omega naught t u t. This particular time function is again oscillatory, but with decreasing amplitude depending upon this value of alpha. So, its plot would be, if this is the envelope, so you have something like this, where the amplitudes decay as e to the power of minus alpha t. So, an exponentially damped sinusoidal function of time. Now, all this differs from the original function is by multiplication by e to the power of minus alpha t. Therefore, according to this rule, all we have to do is replace s by s plus alpha. So, you have s plus alpha divided by s plus alpha squared omega naught squared. So, this gives you a new function of time Laplace transform pair. E to the power of minus alpha t cos omega naught t u t will be s plus alpha over s plus alpha squared plus omega naught squared. We do not have to remember this, because once you know the formula, the Laplace transform for cos omega naught t, whenever it gets multiplied by an exponential factor by that, you should be able to readily reduce this. But nevertheless, let me put this down in our table of Laplace transform and f of t pairs. I will go to the other end of the blackboard, even if our cameraman will frown at this, but let me do that, I will take that risk. So, we have e to the power of minus alpha t cos omega naught t u t will have a Laplace transform s over alpha over s plus alpha squared plus omega naught squared. In the same manner, suppose I have e to the power of minus alpha t sin omega naught t u t. We know that the Laplace transform of sin omega naught t u t is omega naught over s squared plus omega naught squared. So, in that particular function, we have to substitute s plus alpha for s. So, omega naught will remain as before. The denominator will be s plus alpha squared omega naught squared. So, that would be the Laplace transform e to the power of minus alpha t sin omega naught t u t. Visualizing this in this fashion will be very important when you are taking sometimes inverse Laplace transform of functions where a quadratic exists in the denominator. For example, suppose I ask the question, what is the inverse Laplace transform of, say, s plus 1 over s squared plus s plus 1? Suppose I ask this question. Now, note that the poles of this rational function or the zeros of the denominator polynomial are complex. In that case, s squared plus s plus 1 can be put in this form s plus alpha square, s plus alpha whole square plus omega naught squared. If you try to put that in that form, then you can combine, you can decompose this function into sum of two such functions, and then you can readily recognize them to be the inverse Laplace transforms of sinusoidal functions with decreasing amplitude. So, let us go about it. Let's see this. So, s plus 1 over s squared plus s plus 1. First of all, I should write this in the denominator as s plus alpha whole squared plus omega naught squared. Therefore, I write this s plus half whole squared. So, that accounts for the coefficient of s here, s squared plus s plus 1/4, but still you have 1 here. Therefore, to cover that, I will put this root 3 by 2 whole square. So, you observe that 3/4 plus 1/4 is equal to 1, and therefore, we have this the complex conjugate poles of the function are clearly displayed as -12 plus or minus j root 3 by 2. Now, if the numerator has been s plus half, we would have identified this to be e to the power of minus half t cos root 3 by 2. Therefore, let us do that. So, you have s plus half divided by s plus half whole squared plus root 3 by 2 whole squared. This is one term, and what is left behind is another half here. If the numerator has a constant root 3 by 2, then we would have put this as e to the power of minus alpha t sin omega naught t by 2. So, if this had been root 3 by 2 divided by s plus half whole squared plus root 3 by 2 whole squared, then we would have said this to be the Laplace transform of e to the power of minus half t times sin root 3 upon 2 t. But we had only half here, therefore, to cover that you must put 1 over root 3. Then you have s plus half, this term we know is the Laplace transform of e to the power of minus t by 2 cos root 3 by 2 t, and this term will be 1 over root 3 e to the power of minus t upon 2 sin root 3 by 2 t, and of course, the entire thing is multiplied by u of t. That is the f of t, which corresponds to this Laplace transformation. So, this rule of what happens when you multiply the time function by an exponent will come in handy not only in finding the Laplace transforms of certain time functions, but when you are finding the inverse Laplace transform of quadratic factors where the denominator zeros or complex conjugates can be easily be handled in this fashion.